Today I want to talk about silicate minerals. Now, silicates are probably the most important type of mineral that we have. Note that oxygen and silicon are the two most abundant elements in the Earth's crust, so many rocks, many minerals are made of silicon and oxygen. Now, before we talk about silicates, let's talk about the element silicon. On the left-hand side, you see the silicon in its unit cell. Silicon has the same structure as diamond carbon. That is, it's a cubic close-packed structure with silicon in some of the tetrahedral holes. So we have silicon at the vertices of this cube, silicon on all of the faces, and silicon in half of the tetrahedral holes. Now, let's look at silicon dioxide. This is beach sand or quartz. We have basically the same structure. We're going to have a cubic close-packed array of silicon atoms. I've only shown some of them here on the right. But there's a silicon atom at every vertex and in the middle of every face of this cell. We also have silicon in the center of 4 out of the 8 tetrahedral holes. Now, so that the structure of silicon dioxide is identical to the structure of silicon in the placement of silicon atoms. The difference is that silicon dioxide has an oxygen atom between every 2 pairs of silicons. So in a sense, this is reminiscent of the structure of water. All right, let's talk about silicates now. Silicates have a silicon atom that's tetrahedrally surrounded by oxygen atoms. So look again at silicon dioxide. Every silicon in this structure has 4 oxygen atoms around it in a tetrahedron. Here's a silicon atom, 4 oxygen atoms in a tetrahedral array. Si044- is called a neosilicate. We have a silicon atom in a tetrahedron of oxygen atoms, and this is the basic anion. So this is the basic anionic structure, just as carbonate 2- is for the carbonate minerals. And we have in the minerals that are neosilicates, we have a close-packed array of these anions with cations in the holes. Examples of neosilicates are garnet, olivine, and zircon. Now, if you take 2 of these neosilicates, Si044-, and add a proton, lose water, you get a structure that's like a bow tie, where one of the oxygens has been removed and the 2 tetrahedra of silicon are sharing a bridging oxygen. We call structures like this that have Si2O7 6- anions, we call them sorosilicates. We can condense further. We add a little more acid, remove another oxygen atom as water. We can get to chain and ring structures where the anion is some polymer of Si032-. It can be Si032- times 2, times 4, times 5, times 10, whatever. It can be very long chains. But you notice here that I'm only representing on this slide the tetrahedra. You have to envision the silicon at the center of this, and every vertex is an oxygen atom. So in these chains and rings, every silicon is sharing, on average, 2 oxygens with its neighbors. Double chains. We're continuing this condensation process. Now, what I want you to notice in double chains is that we have 2 types of silicon tetrahedra. Here, this silicon is sharing 3 oxygens with its neighbors, and it has 1 unshared. This silicon is sharing 2 oxygens with its neighbors, and it has 2 unshared. So this silicon is the same, has the same environment as the ring and the chain silicates, but this one does not. So we have 2 different types. The anion in these double chains is some polymer of Si4O11 6-. Now remember that this is not a molecular formula. This is simply the smallest unit that we can represent of this long, large material. Okay, so here we see a summary of the silicate structures, starting from the neosilicate that doesn't share any oxygen atoms to the sorosilicate or the bow tie that shares 1. Rings and chains have the same basic empirical formula, SiO32-. Each silicon shares 2 oxygens and it has 2 unshared oxygens. We can't tell the difference from the formula between a ring and a chain. Then we have these double chains. Double chains have 2 different kinds of silica tetrahedra, these that share 3 oxygens and these that share 2 oxygens. We can continue. If you imagine sharing additional oxygens here, we can have a sheet silicate. So sheet silicates consist of sheets of silica tetrahedra where we have 1 unshared oxygen and 3 shared oxygens in a plane. Now generally for the sheet silicates, the unshared oxygens for all silicon atoms is pointing in one particular direction. And this sheet goes on in 2 dimensions. All right, if we share all 4 of the oxygen atoms for every silicon, then we're back to our SiO2 structure. We call this a tectosilicate.